So everything we've talked about to this point in terms of calculating voltage for a voltaic cell has been under standard conditions. And we really haven't talked about too much about what that means, but uh, it's room temperature, right? We know that already. It's also 1 molar though. So the concentrations of the solutions in our beakers have always been 1 molar to this point. Now, we already know that changing the masses of the electrodes doesn't change the value of the cell potential, um, but changing the concentrations of the ions in the solutions does. So if we looked at this as sort of like a battery, if we looked at the reduction potentials of zinc 2 plus and copper 2 plus, um, the direction of flow of electrons is going to be away from the zinc and into the copper because zinc has a lesser reduction potential. So zinc is going to give electrons to copper. Those electrons then are going to be grabbed up by the copper ions in the solution. And here's the important part. That means over time, as I run this battery, copper 2 plus in solution is going to be going away. It's going to be decreasing in concentration. Zinc ions are going to be increasing. So what does that do to the voltage? Well, it actually decreases the voltage over time, which kind of makes sense, right? We discharge a battery, we use a cell phone or a flashlight or whatever, the voltage actually does drop over time as the battery is used. This is dictated by something called the Nernst equation, which you do get on your, formula sheet for the AP exam. But don't worry too much. They pretty much just want you to understand the relationships between the variables. You will not be calculating instantaneous cell potentials under non-standard conditions. So basically just, do you understand the relationship between temperature and voltage? Do you understand the relationship between concentrations and voltage? So that's what we're going to be focusing on. But this is the equation that kind of does it for us. So if you're given this question, find the instantaneous cell potential of the following reaction. And it gives you the reaction there between copper and zinc that's shown in the picture. It gives you the standard potential of the standard cell potential for this cell is 1.10 volts. It says we're at 298 kelvins and we are at concentrations of 1 molar for both the Cu2 plus and the zinc 2 plus. Well, we should already know that since we are at 298 K and we are at 1 molar each for our solutions, those are standard conditions. Technically, also 1 atmosphere is standard, but we're not really dealing with gases here, so it doesn't really matter. But we're under standard conditions. So, therefore, sounds like our standard cell potential would work for our answer, and it does. In other words, the instantaneous cell potential, which is this guy on the left, is equal to the standard cell potential because we're under standard conditions. So why? Well, if we look at these values that we would potentially be subtracting here, R is a constant, T is 298K, F is a constant, N is number of moles, but we're multiplying them by the natural log of Q. Well, Q is just products over reactants, each raised to the power of their coefficients at that moment in time. Well, if we're at 1 molar for products and reactants, right? So for Zn2 plus, which would go on top, and Cu2 plus, which would go on bottom, well, 1 to the first power in this case, because coefficients are 1, or 1 to any power, even if we did have coefficients in this equation, would just be 1. And so Q is equal to 1. And if Q is equal to 1, well, the natural log of 1 is 0, which means that the product of, all of this mess times 0 is 0, and I'm not subtracting anything from my standard cell potential. So that's why all of this goes away if we're at standard conditions. But what if we are not, right? So this is what we're talking about today. Would E cell increase, decrease, or stay the same if the copper concentration dropped down to 1/10 of standard, so 0.1 molar, and the zinc is going to stay at standard conditions? Now, you could reason this out just thinking about this little battery setup. If you don't have very much Cu2 plus ions, and the job of Cu2 plus in this reaction is to get reduced, right, from 2 plus to 0 by gaining electrons, the fewer of them you have, the smaller the voltage is going to be. It's the Cu2 plus is a reactant, so you're bringing down the potential of this battery. So, and that is the correct answer. It will decrease, but we also need to be able to justify that a little bit more specifically using the Nernst equation. So if we have less Cu2 plus, and Cu2 plus is in the reactants, well, if we think about Q, we have only 0.1 molar on the bottom and 1 molar on the top. Of course, that's going to give us an answer of 10. So the natural log of 10, the natural log of any number greater than 1, is going to be positive. And so we are going to be subtracting, right? So forget about all this business right here. Just focus on Q. So as Q, if Q is greater than 1, then there is a number that we are going to be subtracting from the standard cell potential. And in this case, Q is going to be greater than 1 because we have 1 over 0.1, right? So if Q is greater than 1, we are going to say that this will decrease the cell potential. So the instantaneous cell potential will be less than 1.10 volts. And it's not much, it's not a huge difference, but it does make a little bit of a difference. And again, I don't think you're going to have to calculate that, so I wouldn't worry too much about well, you're not going to have to calculate that, but we just have to be able to look at the Nernst equation and understand it, the relationships there. Now, if we flip that around, what does that mean? If I have, you know, higher Cu2 plus and Zn2 plus is lower, well, you know, what does that mean for this reaction? Well, it means just the opposite. Q is less than 1. And natural log of any number less than 1 is a negative number. So if I flip these numbers around, just as an example, and put 0.1 on top, 1 on bottom, the natural log of 0.1 is like negative 2.3 or something like that. So now I am subtracting a negative, right, which would actually cause my instantaneous cell potential to be higher than 1.10, right? Again, not a huge number. I think it's like 1.13 or something like that, but it would actually result in a higher potential. All right, and on to our last segment, our last lesson in AP chemistry, electrolysis and Faraday's law. This one is going to be a little bit more calculation heavy, but it's not too difficult because it's mostly just unit converting. But we are using a new calculation or a new equation. So here's an example of what you might be asked to do. A constant current of 2.40 amperes is applied for 1,500 seconds to a solution of silver nitrate. How many grams of silver solid forms? So if you remember what electrolysis looks like, it's a little different. We could be, for example, plating silver onto a metal spoon. And so we're pushing that in the non-spontaneous direction with a power source, right? So we need to really pretty much just think about the reduction reaction, the half reaction, silver getting an electron added to it to form solid silver on the surface of that spoon. So this question is giving us some units that we haven't really used, at least in chemistry before, amperes. And so let's talk about what this means. If we are we're going to be using the equation I equals Q over T. This is on your formula sheet. I stands for current, so it is measured in amperes, but more importantly for us, amperes is coulombs per second. And then the charge is measured in coulombs. So coulombs are just a measure of charge. And then, of course, T is time in seconds. So if we think about solving for grams of silver, Going way back to the beginning of chemistry, we know that we need moles of silver. And since in our balanced equation, we don't have like a concentration of silver ions, so really the only thing I could get moles of silver from is probably moles of electrons. And luckily we can actually do that. But first we have to figure out the total charge, Q. So we have been given time in seconds, so we have that, and we've been given amperes, our current. So we just need to rearrange to solve for our charge. So multiply both sides by time, we get charge equals current times time. And those two numbers were 2.40 amperes, which of course we want to write as coulombs per second because amperes won't cancel. We're going to multiply that by 1500 seconds, and that's going to give us an answer in coulombs, which is proper for our charge. So it gives us 3,600 coulombs. Okay, now you might be asking yourself, great, 3,600 coulombs, I still don't know how to get that to grams of silver or even moles of silver. But electrons have charge, right? So if we know our total charge is 3,600, there must be a way to figure out how many electrons, or at least how many moles of electrons that would be. And luckily, you will find on your formula sheet Faraday's constant, which is literally written like this, and it tells you that it is 96,485 coulombs per 1 mole of electrons. So if I had 1 full mole of electrons, like this balanced equation shows, 1 mole of electrons, that would be equal to a charge of 96,485 coulombs. Now, clearly I have much less than that, which means I must have much less than a mole of electrons. So it's just a unit conversion. 3,600 coulombs, and then I use Faraday's constant, knowing that 96,485 coulombs is in 1 mole of electrons, and of course I want to cancel coulombs, so it's going to go on the bottom, and that's going to take me to moles of electrons, right? This is a little unusual because outside of electrochemistry, we've never really used electrons in a mole conversion, but really it can easily be used in a mole conversion because that's what the balanced equation tells us. It gives us the relationship between electrons, or moles of electrons and moles of everything else in the equation. In this case, it happens to be 1 to 1. It won't always be because, we're not always going to be going from a charge of +1 to 0. Sometimes it'll be +2 or +4 or whatever. But in this case, 1 mole of electrons is chemically equivalent to 1 mole of silver product. Remember, I'm going to my solid silver. I'm not really concerned with my silver ions, but anyway, it's a 1 to 1 ratio. And from here, it's just moles of silver to what we're looking for, which is grams using the periodic table. And so very simply, ready to plug it in, I get 4.0 grams of silver plated onto that silver spoon or whatever the object was. All right, let's try another one. All right, so here is a practice problem for you to try. A solution of copper 2 nitrate, CuNO32, is electrolyzed to plate an object with solid copper. A current of 1.2 amperes is applied for 10 minutes. Notice there's a decimal there, so that's going to give us a couple, it's going to determine sig figs for us. Find the mass of the copper plated. Now, I will warn you on this one that it's not Cu with a 1 plus charge, so that might change our reduction reaction here in terms of our moles of electrons to moles of solid copper. I will go ahead and give you the answer so you can check your own work. Hopefully you will come up with about 0.24 grams of copper. So give that a try on your own, see if you can get to 0.24, and good luck.